When a professional fast bowler releases a heavy cricket ball, it travels at around 150 kilometers per hour. A projectile of that mass and speed carries roughly 137.6 joules of kinetic energy straight toward the batsman. Without any material to decelerate that force, the energy transfers directly into the skeletal structure. The sudden, localized shockwave is more than enough to instantly fracture the metacarpals and phalanges, the fragile bones making up the hand and fingers. In the 19th century, batsmen faced this velocity with virtually zero protection. Players gripped raw wooden handles with their bare hands, or occasionally wore thin dress leathers that provided zero impact resistance. By the mid-20th century, manufacturers tried to solve this by stuffing raw cotton into leather finger rolls. It provided some cushioning, but cotton acts like a sponge. During a long innings, the padding absorbed hand sweat, doubled in weight, and upon drying, crystallized the leather into a stiff, unusable claw. Modern manufacturers had to solve this specific dual threat. They needed to engineer a barrier capable of decelerating bone-shattering kinetic energy while resisting severe chemical degradation from sweat. The result is the modern cricket batting glove. To understand how they achieve this, we can perform an autopsy on the glove, starting at the primary interface, the palm. Human sweat contains sodium chloride, lactic acid, and urea. Over time, these acidic compounds penetrate untreated leather and break down its structural proteins. To counter this, manufacturers use chemically treated materials like Pittard's WR100X leather. During the tanning process, hydrophobic polymers are permanently bonded to the leather's collagen fibers. This allows moisture vapor to escape while repelling liquid sweat, keeping the material supple. The construction of the glove begins on the factory floor with a process called clicking. Heavy industrial presses punch through this treated leather, separating it into more than 20 precise, flat components. This resilient chemical foundation prevents the palm from turning stiff and slippery. That ensures the batsman can maintain fine motor control and a secure grip on the bat over several hours of continuous play. Moving to the outer architecture, the glove faces a contradiction. It must act as a rigid shield without restricting hand articulation. Manufacturers resolve this using two distinct geometries. The split-finger design divides padding into blocks, maximizing flexibility. Conversely, the sausage finger utilizes continuous rolls for maximum defense. Assembling these geometric shapes requires a technique called post-bed stitching. Technicians sew the outer shell and inner lining together inside out on an elevated vertical column. This allows them to hide the seams and integrate breathable airflow mesh gussets before flipping the entire shell right side out. The geometry a player selects directly dictates their playstyle. Continuous sausage rolls favor batters who rely on raw rotational power and heavy fitting, while split-finger articulation enables players who depend on quick wrist work and delicate touch shots. Inside those carefully stitched finger compartments sits the actual impact payload, blocks of closed-cell high-density foam, or HDF. These foam cells encapsulate tiny pockets of gas that compress upon impact to convert kinetic energy into thermal energy. Over the most vulnerable fingers, manufacturers embed thermoplastic polyurethane, or TPU, inserts. When a ball strikes this rigid plate, it prevents point loading by spreading the localized force evenly across the wider layer of foam beneath it. Some premium gloves take this further, using non-Newtonian smart polymers like D3O. In a resting state, these polymer molecules flow freely, keeping the material soft. But the millisecond a high-velocity impact occurs, the chains instantly lock together, forming a rigid defensive barrier before returning to a flexible state. Despite this advanced polymer chemistry, the actual assembly remains a highly manual craft. Factory workers must meticulously hand-trim these exact foam blocks and rigid fiberglass plates, physically stuffing them tightly into the narrow finger cavities. By layering these specific material densities, the glove achieves a critical balance. It remains lightweight and flexible enough for athletic movement, yet dense enough to absorb and dissipate forces that would otherwise crush a player's hand. The final step in this process addresses a hidden danger. Because the gloves are assembled using high-speed industrial sewing machines through thick leathers and heavy foam, metal sewing needles occasionally snap and remain buried deep inside the padding. To ensure a player isn't injured by hidden shrapnel, Every assembled glove is subjected to a mandatory metal audit. They are passed through an industrial conveyor belt metal detector to flag any stray fragments before the product is cleared for shipping. Soon, the manufacturing process will become even more precise. The industry is currently exploring the use of laser scans to map individual players' hands, allowing factories to 3D print custom elastomeric polyurethane impact foams for an exact, personalized fit. A cricket biting glove is a localized culmination of centuries of material science, of biomechanical engineering, and exacting manual craftsmanship. It is a highly calibrated shield designed specifically to preserve a batsman's most vital tools.